Hello everyone, my name is Claire-Hélène Demarty and this is a joint work with colleagues at Interdigital. So the title of my talk is Energy-Aware Images, Quality of Experience versus Energy Reduction. So this is a kind of follow-up of Dom's talk yesterday on greening of streaming. Although I'm not going to talk about streaming, but still what we try to do here is to see how we can reduce the energy consumption at the end of the video chain. So let me first give you some pieces of context. Climate change is now a reality, and we strongly believe that everyone should contribute. So in that context, for the information and communication technology, well, ICT already accounts for 1.3% of the global carbon emission. And among all the devices that are used in the video chain, televisions represent already up to 50% of the energy use. And when one knows that there exist more than 2 billion televisions worldwide, it's quite obvious to see how a small amount of energy reduction on each display would already account for a large amount in total. Well, it already exists green metadata that explain how to apply some global scaling of the brightness, but they are dedicated to backlit displays. And we know that more recent displays, such as OLED displays, enable pixel-wise energy reduction techniques. Which is why what we propose here is to have here another version of the video that, once displayed, will consume less energy. So for this, our proposal is to have a global framework for pixel-wise energy reduction at display site. And this framework will account for more modern emissive pixel-wise displays. And it will be also useful for two different use cases. The first one, in case the artistic intent is of high importance, consisted in reducing the energy as much as possible, but under the constraint that the visual quality is maintained. And the second use case, which is more related to what we have in streaming, consists in searching for the highest quality, knowing that we have a constrained fixed energy reduction rate. So in GEVET meeting in January, we did a first contribution for this global framework, which consisted in proposing to carry the attenuation maps as auxiliary pictures. Okay, sorry. To carry the attenuation maps as auxiliary pictures and to add a new SEI message that will also give some additional metadata to help to understand how to use the attenuation maps. So I'm not going to go into the details of the syntax that you have here. I encourage you to have a look at the contribution. Let me just give you a few samples of the type of metadata that we propose to add. So for example, we are going to say if we need to upsample the attenuation maps, or on which component of the decoded video the attenuation map should be applied, and how, of course, they should be applied. So since then, we add also two new contributions. The first one is an informative document that was proposed in April in GEVET meeting, and which consists in three different things. So first, we showed that the TV settings or the different screen size do not influence the pixel-wise techniques, nor are they influenced by the technology. We also propose a comparison of two of these pixel-wise technology with first the current implementation in green metadata, and also a global linear scaling of the luminance. And we evaluated the transmission cost of the proposed attenuation maps. And in another proposal, this time in green MPEG, what we did was propose a similar syntax, and we proposed to have it defined as a new amendment of the green MPEG spec, and this was accepted by the group. So to give you a first example of how it can be implemented in the framework, we did try to, we used the race method that exists in the state of the art. And this is already, as you can see, an improvement of another technique called ACE for adaptive contrast enhancements. As you can see also, all of them are deep learning based. And the main difference for the RACE technology is that it's the first time that the network is outputs directly the attenuation map, which is then added to the original luminance to provide a reduced luminance. So in our own implementation of the RACE technology, what we did was using the BSD 300 dataset. It's important to note that no annotation is needed. Indeed, it's a self-supervised networks, provided that you have a display model, which in our case was simply the sum of the luminance values to the power of gamma, gamma being the display gamma. So the network is conditioned by R here, which corresponds to the target energy reduction rate. So it is applied directly in the architecture, but it also appears in the losses here. We had 4 different losses. The 2 first ones were quality-driven, with first the mean average error and the SSIM loss between the input and the output luminance. And then we had, as I said, the power loss, which consists in computing the difference between the power of the reduced luminance and the reduced power of the original one. And we added also what we call total variation loss, which is computed on the gradient of the attenuation map, and which should improve the smoothness of the maps. Our training was done in 2 steps. In a first step, what we did was only using the 2 quality-driven losses. And then in the second step, we add all the 4 losses in a weighted average sum. Okay, so let me now show you some results. So you have here 3 different metrics. From left to right, you can see the PSNR, SSIM, and LPIPS. And on the x-axis, what you have is the reduction rate that goes from 5 to 60%. So a first conclusion is obviously that when you increase the reduction rate, you will decrease the quality, as you can see here. But still, if you have a closer look at SSIM, it seems that up to 10%, you do not lose a lot in terms of quality. You even have quite high values of qualities. And even up to 40%, I don't know if you can see here, but you achieve 0.96 in terms of SSIM, which is still quite high. And at the bottom of the slide, what you can see is a comparison of the computed power after the reduction in green here, still against the target energy reduction rate, and in red, it's actual real measures that we did using a watt meter. So as you can see, we do not have a perfect correlation between the two sets of values, which means that we certainly need to investigate more the display model that we were using, and which is quite simple and apparently not suitable for the type of displays that we use for our testing, which was an RGBW display. So here I'm showing some qualitative results. You have on the first column the original images, and then 3 versions of the reduced images from 10 to 20 and 40%. And on the last column, you can see resulting attenuation maps that were applied on the original image. Going further, results on video sequences. So here what I'm showing is a comparison between race and a global linear scaling. So you will have the 2 different techniques between the bracket here. And I'm giving VMAF and PSNR values. So obviously what you can see is, once again, up to 20% we are doing well because the VMAF values are very high, and we are doing better than linear scaling. Sorry. Here. And again, when you increase the reduction rate, you lose in terms of quality, but the difference between the 2 techniques is increases with increased energy reduction rates, meaning that race is doing better for higher reduction rates. Okay, to conclude, so what is in the paper is a proposal for a global framework for pixel-wise energy reduction at display side. So what I also showed you was a first implementation of the framework. We have a process ongoing in the standards with an amendment of the Green MPEG specification. And for future work, well, we want to work on 2 different axes. First, obviously, try to improve the technologies for reducing the energy consumption of such images. And the first point is certainly to try to see how we can improve the display model. And the other axis of research is obviously to continue the process in the standards. So I put here the agenda. As you can see, we have a committee draft that is expected for the end of August this year. And hopefully we will have a standard in 1 year from now. So this concludes my talk, and I will be happy to answer to your questions.
Thank you very much. Very interesting. So we have time for 1 question, please.
What was the raw wattage values saved with the targets you were achieving as far as on the Sony, where you it was like a 20% energy savings, and I was just kind of curious what that translated it for raw energy.
Okay. So if I can go back a little. And if you have a look at this graph here, so 20% is here. So as you can see, more or less, we have half the expected energy in terms of saving for 20%.
Okay? Okay, thank you very much again.